All of the ideas that we have been learning in this unit thus far have really been leading up to developing a strong understanding of stoichiometry. So in this tutorial we want to wrap our heads around what stoichiometry is, and in particular we want to see how those numerical coefficients that occur in balanced chemical equations, we want to see what role they play in relating the amounts of chemical compounds to one another. In a subsequent tutorial, we are also going to learn how to solve stoichiometry problems. And this is a skill that will be important in this course, obviously, but also in future chemistry study. So the numbers in chemical equations are called the stoichiometric coefficients. And what they do is they relate the amount of reactant to the amount of product in those chemical equations. Now, stoichiometry, we want to get an understanding of what is it used for, what is it about, why is it so important. If we think about chemistry on a larger scale, let's say using a chemical process or carrying out a chemical reaction to produce something in industry, so to manufacture something. One of the things that it would be important to know is how much product you're going to be making. And understanding the concepts involved in stoichiometry allows us to make predictions about how much product will be formed. But again, if we think back to an industrial setting where they're using a chemical process, and they're really interested in efficiency, so making the most of what they have and probably trying to maximize the number of dollars that can be made in a given process. And so when we start to think about that, one of the really important things that comes up, or one of the important ideas that comes up, is that you want to figure out how much of the reactants or how much of the starting materials you need in order to produce a target amount of product. And that's important in terms of, as I said, maximizing dollars, because you don't want to use a ridiculous amount of a given reactant and end up just wasting it if it's not going to be used. It's really important in terms of the environment, because again, if you end up wasting a whole bunch of something that is potentially toxic or is very rare and hard to come by, that's bad for our environment. And so stoichiometry and understanding the concepts associated with it allows us to make calculations like that. And sort of along that same sort of note, we can use stoichiometry to figure out how much of one reactant is needed to completely react with another reactant. And so again, in terms of maximizing efficiency from a dollars and cents perspective, that's good business to completely use up both of your reactants as best you can. And it's also, I think, good from an environmental perspective in that we're certainly limiting the amount of waste. And so understanding these concepts related to stoichiometry, sure, they're important for us, and they're important for us within the confines of this course, but they also have importance in many other processes or many other maybe facets of life. Now, really the key thing that comes out of stoichiometry is we talked about the stoichiometric coefficients, so the 2 here and the 2 and the 3, those are the stoichiometric coefficients. And what they represent, we've seen previously, they can represent the number of molecules or formula units or atoms involved in a chemical reaction. And so this would be like 2 formula units of KCl3 lead to 2 formula units of KCl and 3 molecules of oxygen. But more importantly for us now, and kind of the approach we've been taking throughout the unit, is we're going to look at these from a mole perspective. And so a mole ratio then is what we can use to relate the amounts of things in a chemical equation using moles. And so this first question here will help us to work through this idea. When it says how many moles of oxygen are produced from the decomposition of 1.76 moles of potassium chloride. So we want to see how much of this is produced when we know that 1.76 moles of this breaks down. And so I have the mole ratio set up right here, and I split it into the known ratio and the unknown ratio, and we make these two things equal to one another. So the known ratio is based on the information that is given in the chemical equation up above. And so we are told from this chemical equation that for every 3 moles of oxygen that are produced, 2 moles of KClO3 break down. But that's not what the question is asking. The question is saying we want to know how many moles of oxygen are produced if 1.76 moles of potassium chlorate break down. And so that's where the unknown ratio comes in. We put whatever we are looking for, and so we're looking for the number of moles of oxygen, and so I'm going to let X represent the number of moles of oxygen. And we take the information that we are given, the 1.76 moles of potassium chlorate, and we put those two factors on in what I call the unknown ratio. So mostly called the unknown because our unknown X is on this side. And now we can solve this, this ratio for X, and that will tell us the number of moles of oxygen that are indeed being produced in this situation based on the fact that they will react in this way. And so to solve for X, I'm going to multiply both sides of the equation by 1.76, and after multiplying both sides of the equation by the 1.76 and isolating for X, I end up with 2.64 moles of oxygen. And just before I explain that, typically I would like you to include your units as you go here, and so include the number of moles, but also typically you're probably not even going to write this step out. So you could jump right to this line and say that we have 2.64 moles of oxygen. And so why is that the case here? So we know that for every 3 moles of oxygen that are produced, 2 moles of KClO3 are needed. But, like I said before, we don't have 2 moles. We have 1.76 moles of KClO3, and so now we see that in a situation like that, where we have the 1.76 moles of KClO3, 2.64 moles of oxygen are produced. And now we begin to see how a balanced chemical equation can be used to relate the amounts of stuff, or the quantities of stuff, for the substances in that chemical equation. And so we get a bit of a sense of what a mole ratio is and how it connects the different parts of a chemical equation. And we're going to see that when solving stoichiometry problems, using mole ratios is right at the center, or is really a really important thing. But the nice thing about solving stoichiometric problems is that it's the same approach every time. And so, as I said, the number of moles are key. And we're going to use the grass check method, and you will see that when you take a look at the example problem in the tutorial on D2L. But I just want to quickly highlight what the analysis or the steps involved in solving a problem like this. And so we have if you start out with the mass of one substance, and so we know that it's really important in order to be able to connect things using a chemical equation that we work in moles. And so we convert our mass of whatever we have to number of moles, and we can do that using the molar mass. And so now that we have the number of moles of one of our substances, we are able to convert it to the number of moles of something else within that chemical equation by using a mole ratio. And so finally, using the number of moles that we just calculated from our mole ratio, we can convert that back to a mass, and this is often, at least in the first stages of doing stoichiometry, what we will be asked to find. So we can convert it back to a mass using the molar mass. And so you see here that you're going to see this pattern over and over and over again, where you start with an amount of something and it needs to be converted to moles. And then you can relate the moles of that thing to the moles that you are trying to find using a mole ratio, and then you can take the number of moles of the thing that you were trying to find and convert it to whatever amount, let's say a mass, using something like a molar mass. And so, as I said, this question will be examined in a separate tutorial whereby we will kind of put this strategy that we just discussed to work. So hopefully from this tutorial you see that stoichiometry really is about using the balanced chemical equation and mole ratios to relate the moles of one thing to the moles of something else so that you can determine whatever it is you need to determine about a process.